The topic for today is going to be influence of a variable or a function. The intuitive idea is we have a function from -1, 1 to the power n to -1, 1. We think of it as a function with n variables. And we want to figure out how important, impactful is a particular variable in getting the function out. If I look at x1, is x1 going to determine the value of function more as compared to x1 or things like that? One of the natural places where this kind of a impact or importance is used is social choice theory, where the Boolean functions we are talking about, you can think of them as a voting. That means x1 is the vote of first person, x2 is the vote of second person, xn is the vote of nth person. And then f of x1 to xn tells you what is the vote, the total vote, or what is the output of your voting procedure. What is the most natural F people use as a voting rule?
Majority.
Right. Mostly people use majority, but that is not always true. You can use different things like that. We will go into detail of social choice theory, but yeah, again, it is important, or it is a useful notion where we say whether x1 matters when we calculate a function, whether x2 matters when we calculate the function f, and things like that. And for that, there are many ways to capture it. There is no single way to capture it. The way we are going to capture it is by this mathematical definition, which is called influence of a variable. It is denoted by influence I. And how do we define it? The one way to think about it is, okay, yeah, I should probably introduce a notation first, an important notation, and then I will define the definition of influence. Given an input x, this is another input where the ith bit is flipped. Okay. So x, what is the Hamming distance between x and x XOR I?
1.
1. Exactly. So everywhere these two things look the same. On the ith place, the xi is flipped. If xi was 1, then it becomes -1. For example, if my input was this, and I ask, yeah, so this I, do we count it from 0, 1 to n -1, or 1 to n? Let's say we are counting it from 1 to n. And then if I say this, then this is the answer, because I will flip the third. Right? Now, intuitively, if ith bit is important, then what would you think will be the relation between these two?
They shouldn't be equal. I mean, they should not match at most
Right.
of the points.
Very nice, right? So if if ith bit is important, then fx should not be equal to f of x XOR I, but the question is for how many x's or for what x's? We would like to say that for many x's, if f of x is not equal to f of x XOR I, where ith bit is flipped, if they are not equal, that it seems like ith bit is playing an important role in calculating. Now we can formalize it. With this intuition, we can define what is going to be the influence of it. The ith influence, that means the influence of the ith variable in f is going to be the probability that fx is not equal to f of x XOR I. Now, what is this probability over? What is the probability distribution I'm talking about?
Uniform.
Correct. This is the, yes, this is the uniform distribution. That means every x is picked with equal probability. In essence, in some sense, this is just counting the number of x's such that fx is not equal to f of x plus. Right? That is what this definition is doing.
Sir, can you just go to last page? Just I look at the definition.
Sure.
So what is this XOR I?
S x XOR I is the another input where you just change the ith.
Okay, so this. Okay, this is with this. What do you mean by flipping? I mean, when we have x in form of 1 minus 1, then I can flip.
Yes, so this is only for Boolean hypercube. Right? If your input is in plus minus 1 to the power n, you look at the ith bit, and if ith bit is minus 1, you change it to 1. If it is 1, then you change it to minus 1.
Oh, okay, I see. So there you are changing a lot of inputs. And for all those inputs, it should happen.
I am changing just
one. I was thinking that symbolically how you are flipping, but that is not the case.
Okay. Yeah. So for every input, I can define x XOR. This is just a notation. Right?
Yes.
And then this definition is intuitive.
Yes.
Let's see. I already mentioned that this need not be the only definition, but let's see how this is in some sense natural, but in some sense not natural. Again, I want to emphasize that there are many ways to think of the influence. This is just one way, but this one way is going to be helpful in proving some results and in some applications. That's why this definition is important. I have given one intuition. You are counting the number of x's and then basically normalizing it, dividing by 1 to the power 1 by 2 to the power n to get the value of influence. This is another way to define it instead of probability. Now, what if influence of f is 0 for the ith variable? What does this mean?
We can altogether ignore that bit. We
Sorry?
do not know the value of that.
Function is independent of the xi variable.
Very good, right? Function is independent of I. That means in the truth table, even if I remove the ith column, it doesn't matter. my function still remains the same. That basically means that in the Fourier expansion, my xi will never appear. Again, okay. Now it is not, at this point is not clear whether the Fourier expansion will have, but you would like to believe that, right? So from the truth table, it is clear, right? In the truth table, whenever I flip, the function value doesn't change. That means the ith column is redundant. I can remove the ith column and still the truth table will be fine, will be consistent. That you agree, right? Yes, no?
Yes.
Right? So that is quite clear. That ith bit is never used in computing the function. The function only depends on other n minus 1 bits. But intuitively, that should also say that this should imply, at this point, it's a question. What should it imply? It should imply that xi does not appear in the Fourier expansion. That is also something which you will expect. Yes or no?
Yes.
Yes.
You remember the Fourier expansion?
I think in order to prove it, we could construct an input such that the results would be different.
Sorry, we could?
We could construct inputs such that it could show that xi is influencing it. In order to prove this.
So we will do a more general approach. We'll take a more general approach. What we will do is we will come up with a formula for influence in terms of Fourier coefficients. So that is what we have been doing till now in applications, right? We take our problem, it is in terms of standard basis. We say, what does it mean in terms of Fourier basis? And then suddenly we get answers. Right? I understand what you wanted to do. You were saying that we kind of, if xi appears in some monomial, you are going to create an input where such that xi will matter for that particular, right?
Yeah.
Right. So that is actually easier in a 0-1 thing. In -1-1 basis, it is slightly hard.
Okay.
Right? So
yeah, for this proof, can we approach it this way that in the standard basis, when we express f in the standard basis form, then if we consider the ith bit, then either it is going to be of the form 1 minus xi by 2 or 1 plus xi by 2. Yeah. So now if I say fx is equal to f xor I, then I can take that outside, and all the remaining inputs, I mean, for given x, I can take them outside. And then that 1 plus xi by 2 and 1 minus xi by 2 will get cancelled. I mean, it will just give me 1. So basically...
Good. That's a perfect. So what you are doing is all the 1 inputs, remember, or actually all the inputs now, because the output could be 1 or -1, you are grouping them in these pairs of x and x plus I, right? X XOR I. And then the indicator terms of these, since the coefficient is equal, everything else will remain same. So some polynomial of x1 to xi minus 1, and then up to xn will remain, and then you will get 1 plus xi by 2 plus 1 minus xi, right? And then your point is xi disappears. Am I correct? This is what you are proving. This is how you are proving.
Yes.
Good. This is a perfect way to prove this. So we will prove it in a more general sense, in the sense, as I said, we will capture influence I of f in terms of the Fourier functions. Right? And so this in some sense is showing that this definition is a sane definition, right? It is not insanely ridiculous definition of influence of a variable, right? But then it is not completely intuitive too, right? Let me take an example. F of x is equal to xn. G of x is equal to parity, which means x1, x2, xn. Right? This is, what do we call these functions? Do you know? Fx equal to xi? These are called dictator functions. I might not have introduced this terminology, but these are the functions which depend on just one bit. They are called dictator. Right? And this is parity. Now, just looking at the functions fx is equal to xi and gx is equal to x1, x2, xn, where do you think influence of the ith variable should be greater, in f or in g?
In F.
Sounds natural, right?
I think it should be equal in both.
It should be
Equal
No,
in
no.
both.
Because you are calculating it through the definition, right? Right. If you are, yes, so, right, correctly. So our definition will say that influence I of f is equal to influence I of g. But if I had not defined the influence beforehand, you would think that, dictator function just depends upon I. I is the only thing present. So influence of I should be much more in f as compared to g.
I mean, even intuitively, we could think that flipping xi will definitely change both of the results of the function. So maybe that could.
Right. So once you align yourself to the definition, then you will see that these influences are equal, right?
Yeah.
But again, before you make this definition or you give intuition for that definition, if I had asked which function has more influence of ith variable, you would say f, right? Before the definition was that is the yeah. So what I'm saying is the definition of influence is the same definition, but it is not the only definition, or it is not a perfect definition. That is what I'm saying. It is one way to capture how influential ith variable is for f. That is the only thing I'm one way to capture influence of. When I say here influence of I mean the English definition of influence, not the mathematical definition. Mathematical definition is fixed. Right? Let's go to our next objective. Once we know that this is a decent definition, not perfect, but this is a decent definition. Let's see what we can do with this definition. First thing we would want to do is find Fourier expression for influence. How can we do it? Let's try to do it. Let's see. We want to find this one. You want to write it in terms of Fourier coefficients. How can we do it? What are the ideas?
Just an idea that say supposing if you flip the ith bit, then basically you are creating another function g, which is which is obtained by f of x1, x2, and at xi it is replaced by minus xi.
Very good.
So
let's define g of x to be equal to f of x XOR I, right? Then what is the Fourier coefficient of G? What are the Fourier coefficients of G? This is summation over S G hat S chi Sx, right? Now, what is the relationship between G hat S and F at S? This is already just told to us. Either it will be F at S or it will be minus of F at S. When will be when will it be F at S?
When I is not in S.
And when I is in S, then it will become minus of S, right? This is clear because we are just changing, flipping that amounts to changing xi to minus xi. Correct? Right? Then we want to figure out when is fx not equal to gx. You have captured the Fourier idea, but there is a general way in which such probabilities can be converted into a mathematical expression. Right? Let me just say how this is done, and you can verify. Now, fx not equal to gx is a weird quantity to write in terms of mathematics, but this is also equal to fx minus gx by 2 whole square. Do you agree with this? Just this, or what I should say is that it doesn't make it is equal, but this quantity is 1 if fx is not equal to gx, and 0 if fx is equal to gx. Correct? Again, remember, this is all happening because my range is range of f and g is -1 comma. That is the reason why I can say so. Do you agree with this? Not agree with this? Am I doing a mistake?
Should it be fx instead of 1?
Sorry?
Should it be fx instead of 1?
No, I'm squaring.
What
right?
is the value of?
I'm squaring, right?
Oh, okay.
So fx minus gx will be equal to either 2 or -2. If fx is not equal, if fx is equal to gx, then this quantity will be 0. This is clear, right? And if fx is not equal to gx, then this will be -2 or 2. Divided by 2, it will become -1 or 1. You square it, it will become 1. Confusion. Sorry, I think it's kind of clear. Why are you guys stuck? Can people raise their hands who are not clear about this? Okay, then just say, right, that this is simple. This is fine. Okay, if this is the case, then what is the expression for probability of x fx not equal to gx? Can I write it as an expectation?
Expectation of this quantity.
Exactly. Right? This is because this is an indicator wave. of the random. This is an indicator of this event. That's why the probability of an event is just the expectation of the indicator variable. Is this something which needs to be explained? Anyone who has a doubt about this, or everyone is fine with this? Okay. Yeah. So what is, call this quantity some random variable y. Expectation of y is summation over the possible values which y can take, probability y equal to y. Now in this case, this is just a 0, 1 variable. That means this will become probability that y is equal to 1 times 1 plus probability that y is equal to 0 times. This will get cancelled. That means expectation of y is just equal to probability that y. This just follows from the definition and the fact that your random variable is only taking two values, 1 or 0. This means what you are interested in is influence, is the expectation of fx minus gx by 2 whole square. Now, I think Aditya or one of the other person already told us what is the Fourier expansion of this. Can you tell me what is the Fourier expansion of fx minus gx by 2? Remember, G is f of
It would
X,
be
X,
f at s when I is in not in s, and it would be 0 when I is in s.
Actually, no. The terms which will cancel is when there is no I.
Yeah, there's a minus sign.
Yes. When I is not an element of S, then the coefficient in F and G is the same. They will cancel out. If I is element of S, then those two coefficients will add up and 2 will cancel. Remember, we said this. G at S is F at S when I is not element of S. That means when you do Fx minus Gx, these terms will cancel. But when I is element of S, this will be added. And you will get this. Sounds good? Call this function h of x. Then what is expectation of hx square? This you know.
Summation over s. Summation over s f at s square.
H at s square, right? What is this? What is this theorem?
Parseval's.
Correct. Generalized Parseval or something. And now we know h at s is 0 if I is not an element of S, and if I is element of S, then it is just f at s. This gives the Fourier formula for influence. And this seems very natural, right? What you have done is just taken all the coefficients which contain xi and you have squared and added. That is the influence of the IF. By the way, this also shows something which you have already shown, that if influence is 0, implies xi does not appear in the Fourier expansion of f. Questions?
Yeah, so how do we get from the Parseval's theorem to the one in the box?
So this circular box is okay.
Yes.
Now you look at the definition of Hx, right? H of x is summation I element of capital S f at s chi s x, right? And the Fourier expansion of any function is unique.
Okay, so only those terms contribute where I belong to S.
Correct. And everywhere else the function is zero. Everywhere else the Fourier coefficient is.
Yes.
H at S is f at s if I element of S 0. Right? This comes from this side. There cannot be any other expansion. And now, cool. We got a Fourier formula for influence, right? We have gotten a Fourier formula. I just wanted to define one more thing, which is used many a times, which is called the total influence. The total influence of a function is not surprisingly, it's just sum over I individual influences. At this point, don't worry about what is the use of it, what is the meaning of it. This is called the influence. This is the definition. Is this clear? If it is clear, then tell me what could be the maximum value of influence of it.
N.
Who was this?
Watson.
Watson. Yeah, Watson. Why is it n?
I mean, the parity function, if you look at it, that is an example of.
That's not an argument that it can be at most.
Yeah, yeah. Right? Yeah. Because each of the influences, each of the input can have a maximum influence of 1. So
good.
It is bounded.
Yes. Then there are n variables, right? So every influence is a probability. That means influence lies between 0 and 1. Now there are n variables. That means total influence will lie between anyone?
0 and 0.
Right? Good. This takes care of influence, right? We saw two things. We saw that the influence of the ith variable is f at s square. Then what will be the Fourier formula for influence? How can I write influence in terms of f at s?
Summation over all I, summation over all S, which contain.
Yeah, but you can simplify it, right?
Except S is equal to 5, summing over all Fourier coefficient.
No, that would not be counting correctly, right? How many times f at s is appearing?
The number of variables, the number of elements in S, mod S times.
Correct. Is this clear? Do I need to explain this expression, or now once I have written it, it makes sense? Notice in the equation 1, you pick a particular S, your favorite S. How many times will f at S appear? It will appear in this summation equal to the cardinality of S. If S is 1, 2, 3, then in this summation 1, f at S will appear for I equal to 1, for I equal to 2, for I equal to 3. Right? That's why it will appear cardinality of S. Hence, the proof of equation 2 is questions about this? Intuitively, what you would want to remember from this expression is that high level Fourier coefficients contribute more to influence. Right? Think of it this way. If you look at any Boolean function, what do we know about this quantity for any Boolean function? Summation f at S square?
2 to the power n.
No.
Sorry, it's 1. It's
1. 1, right? This quantity is equal to 1. For any Boolean function, summation f at S square is equal to 1. In some sense, you have one weight which you are distributing between different subsets or different monomials. If you put more weight in the small or low level Fourier coefficients, low level means low Hamming weight, S is equal to 1, S is equal to 2, S is equal to 1, 2 or something. If you put your weight in those low level Fourier coefficients, influence will be small. If you put your weight in high level Fourier coefficients, like S is equal to 1, 2, up to n, 1, 2, up to n minus 1. If you put your weight on those high level Fourier coefficients, influence would be high. Ultimately, you have same amount of weight to distribute between all the sets. Remember the picture? You always draw this picture, right? This is the Boolean hypercube. This is set 0, or sorry, I should not say set 0, but this is phi. This is set 1 to n. These are high Hamming weight or high levels Fourier coefficients. These are low level coefficients. And the ones at the low level contribute less to the influence as compared to the high level coefficients. This is clear from equation. This intuition will be helpful in understanding influence and yield.
So basically, you are trying to, I mean, we can picture f hat S square. I mean, something like a probability distribution on.
Yes, yes, very good point. This is actually, you can call it Fourier distribution. This is a distribution over all subsets where subset S is picked with probability f. Just a small piece of information or a nugget. Many of the places where quantum computing has an advantage over a classical computing is because on a quantum computer, it is easy to sample according to this Fourier distribution. You want to check some property of function f. that might be your problem on a classical computer or a quantum computer. What you are given is a black box access to F. What does it mean? You have a black box F, you are given X, you get F of X. Now using this, you want to figure out some property of function. I'm not going to talk about which property, but some property of function F. Now you can sample according to this probability with this black box. This is in some sense the standard probability distribution. But this is not helpful. In quantum, using the similar quantum black box, you can sample according to this Fourier distribution. And that way you can figure out the properties of F much more nicely, and that exhibits itself as a quantum advantage. This is a side note, this is not part of the course. So don't worry about it if you are scared of quantum computing or something. Just for some people who are interested in quantum computing, I want to make it a point that this is an important concept, and this is the reason why you get quantum advantage. Precisely because you can sample according to the Fourier distribution. If you're not interested in quantum computers, please ignore. I'm sorry for taking this time. But yeah, completely correct. This is a very, very important distribution. Distribution over the subsets now. Instead of the inputs, this is a distribution over subsets. Cool. What are we going to see next? All of you have heard of derivatives? Yes, no?
Yes.
Yes, correct. We are going to define derivatives even for Boolean functions and expect that they satisfy many of the properties which we know of derivatives in our real. Right? Our real world, we have functions from real numbers to real numbers, and we take their derivatives. We know many nice properties of them. Now for Boolean functions, you have to define it differently, but still we expect that some of the properties are satisfied. Let's see how to define derivative of a Boolean function. You see that it is not straightforward. It is not, we can't define derivative as we define for a real function. There is no concept of limits. We can't say, oh, as your two inputs get closer to each other. We can't. Right? That's why it has to be defined this way. The ith derivative of f is defined to be f of x. This is a weird notation. What I'm saying in this is that the ith bit of x is set to 1.
And what about the rest of the bits?
Sorry, rest of it remains same.
Where exactly does this x come from?
Sorry, I should have put it in the, so
Okay.
DIF is in itself a function, right? Yeah, okay, let's just consider it to be, yeah. 2 minus 1. Okay. So you take a string. The string will tell you the values of x1 to xi minus 1 and xi plus 1 to xn. For xi, you substitute this value and then divide. this is the way we are defining derivative. Another way in which we could have defined derivative would have been obvious, or some way could be like this. Right? Fx minus f x changed at I divided by c. But it is not defined like that. This is called the Laplacian. The derivative is defined like the way I have shown you, and I will show you why that is this. Even the Laplacian is studied. Even this is studied. But for us, derivative will be this definition. Is the definition of DIF clear?
So DIF, the domain should be -1, 1 to the power n, right?
So again, as I said, think of it as I'm specifying the values at from x1 to xi minus 1, and then xi plus 1 to x.
Okay.
Okay. You can think of it as a function from -1, 1 to the power n to -1, 1. Completely fine.
So Laplacian will be -1, 1 to raised to n, right?
So even Laplacian, even derivative, you can think of it as -1, 1 to the power n to -1. Right? Okay.
Sir, I'm actually not sure about this, but when you write -1, 1, power n minus 1, then does that imply that a DIF is independent of I?
DIF is going to be independent of x. You can see from the definition that it does not depend on x. Right? Because if I had a the way I have defined it, I'm setting xi to be 1 and then setting xi to be -1. So whether xi is equal to 1 or xi is not equal to 1, it doesn't matter. As Ashish pointed out, but if you talk about Laplacian, that depends, right? If the function value changes, then it might be minus of the quantity. But the derivative actually does not depend on this. Okay, and let's I think, yeah, let's keep this as a function from -1, 1, 2, so that all of the things are in -1, 1 to the power n to -1. That is probably nice. Let's keep it. Okay, everything will be n variable functions outputting a Boolean. Okay, let's not worry about this.
So there is one question, sir. In Laplacian, when you are writing f x XOR I, that means you are replacing xi by 1 minus xi.
Not 1 minus xi, minus of xi.
Oh, sorry, minus of xi.
So what is the question?
Yeah, that I was confirming, because when XOR I was initially defined, it was not symbolic.
Okay.
Here it is symbolic.
So derivative, now the derivative is clear. Why is it nice? Let me tell you a few reasons how derivative is nice. You will see tomorrow. We will use derivative to prove some properties. But one of the things is that this is very much like the real derivative, in the sense that as a function, di of f plus g is going to be equal to, what do you guess?
F plus dig.
Yes, DIF plus DIG. And you can check that actually very easily from the definition. Okay. What about DI of...
Sir, f plus g isn't exactly a Boolean function, or y plus b being the plus in that Boolean multiplicator.
Oh, yeah, sorry. This definition is valid for all functions of this.
Oh, this is R.
Right? But it will work for Boolean functions.
Okay.
then I can write di of CF is equal to
C times DIF.
yes. Again, if you don't see it clearly, it's okay. But if you sit down for 2 minutes, you put things there in the definition, you will see that. These two are easy consequences of the definition.
I think the multiplicative property should also hold. Di of Fg equals to Di of F.
No. You can try. It won't. Okay. Now, let me ask, what is the di of chi-s? You know chi-s, right? Parity function, partial parity.
If I does not lie in S, then it will be 0.
Correct.
And if I lies in S, then
The input also needs to be
If
satisfied.
I
with
lies
what
in
X
S, then
we
it
have.
will be chi of S minus I. Okay.
Yeah.
Correct.
Then minus, I mean, the set subject.
Phi of S minus I.
Again, this is something which directly follows from the definition of the function. Right? What you will get
Excuse me,
is
sir, can we just quickly go to the last page?
yes. Sorry,
It's fine now. It's fine.
it's fine, right? Because what you will get is product I element of S, where J element of S such that I not equal to J Xj times 1 minus product J element of S I not equal to J Xj times minus, right? Because you are fixing Xi to be 1 in the first case, minus 1 to be in the second case, and then you are dividing it by 2. Right? This will give you pi J element of S I not equal to J Xj. These two terms will add, 2 will cancel with 2. This is chi of. Good. This tells us what is di of f in terms of the Fourier expansion. Remember, the derivative is linear. And
So
I
it's
have
just
given
like taking the derivative of a polynomial.
very good.
It looks like
Exactly. Exactly. So let me give me the expression for DIF, right? What did I do? I said that f di is linear, and I have defined di on each of the basis elements. That means I can talk about di of f also. That will just be equal to summation over s f at s you have to correct me. So few places I haven't defined. What are the corrections needed in this formula?
for phi, I mean the chi of phi, it will be 0. Because it will vanish.
You mean f hat of phi will be 0?
No, because no, not f. I mean
DIF of the hat of DIF of phi?
You have
You
to
mean
include
no.
I does not belong, I belongs in S, and instead of chi of X, there is chi of S minus I.
good. You will only worry about things which had I.
Yeah.
And then this,
Yes minus I.
right? And as someone already noticed, This is the usual definition of derivative. For example, if f of x was x1, x2 plus x3, x2 plus x1, x2, x3, what will be d1 of f of x? If I want to take the derivative with respect to x1, what happens? What happens to x1, x2?
x2, I mean, it reduces to
What about x3, x2?
Goes to 0.
Yes. Derivative of x3, x2 with respect to x1 is 0. This is what you would expect in the real world, and the way we have set the definition of derivative, this is going to happen in the Boolean.
Why it is all derivative? It is quite different than the usual derivative.
So I don't know which one you are claiming to be your derivative. You mean the derivative on the Boolean domain?
It's a real domain I am talking. So, I mean, one big difference is there variables may appear. I mean, n variables may remain here. One variable is certain with one.
Yes, yes. That is why it is good. It is not at all clear that we could have had a definition of derivative that will behave so nicely with respect to the polynomial. But there is a definition.
Does this have some similarity? Something why it is called derivative?
Oh, this is the discrete derivative, right? If you think about it, if you look at this box, what is 2? 2 is in some sense the difference between the value of xi at 1 and xi at -1. It's just that I can't take the limit. So I'm taking the minimum possible difference, which is allowed in my domain.
Yeah, in terms of discrete derivative definitions.
Yes. This is exactly discrete derivative. This is how I would define discrete derivative. I think the only confusion could be whether you want it to be the Laplacian kind of a definition or the derivative, or the DIF or LIF. Which one is the correct? And the whatever things we did next, it kind of shows that DIF is also important. It's not.
Yeah, it is not clear why replacing one is important or flipping xi.
Yeah, so
replacing xi is important.
Yeah, so one of the way to think of this thing is that if you wanted to talk about derivative and you look at the Laplacian definition, actually, if xi was -1, then you should when your value changes from -1 to 1, you should divide by -2 instead of 2. That's why for derivative, the definition above is the correct definition. It should not be like that. That's another way to kind of convince yourself. But yeah, so a derivative is very, very natural. It is easy to take the derivative. And one of the most important reasons why derivative is important is because my f can be written as xi times di of f plus ei of f. What is ei of f? This is the expectation of f over xi. Other way to say it is, this is f of x plus f of x XOR I divided by. This is the expectation of. And if you notice, the important property here is that di of f and EI of f, both of them, this was noticed by one of you, does not depend on xi. So many of the properties are actually proved using induction, where we break f into this this equation. Right? This is a good way to simplify your function. Go one level below in your function. Express f simply in terms of things which do not depend on x. And Fourier expansion wise, DIF and EIF are very, very clear. In DIF, we take all f at s's where I is element of S. We pick all S such that I is element of S. In EIF, we take all S such that I is not element of S. By definition, EIF is not dependent on xi. And in DIF, since everything depends on xi, I can just take xi to be common outside. The remaining part is again independent of xi. Sorry, I have not given you the application now. You will see the application tomorrow. But just with the definition, I'm trying to intuitively tell you why this derivative is important. Because this allows us to break the function into simpler parts. And then we can use induction and things like that. This you should remember, these kind of nuggets you should remember when we encounter functions want to prove. Derivative clear, like we define derivative in the real case, we define derivative for Boolean functions, and it very naturally corresponds to the Fourier expansion. Now let's see a simple advantage of defining DIF. Remember we talked about influence? How can we write influence in terms of DIF? Can we write influence in terms of DIF? This was probability over X.
So DIF square.
Very good. This is expectation of DIF square. Remember, we wrote it as expectation of fx minus f of x plus I divided by 2 whole square. But DIF whole square is same as fx minus fx plus I divided by 2. Right? Because DIF will either be equal to LIF or minus LIF. This one was LIF. And we know that DIF is either equal to LIF or I should just say this. Again, we are using the fact that our F is outputting something out of plus minus. This is not difficult to check. This is fine. Now, there are a class of functions, very natural class of functions like symmetric functions, which are important in the study of Boolean functions, which are called monotone functions. What is a monotone function? F of x is greater than or equal to f of y if x is greater than or first job is you look at this definition and tell me what is not true. This I am defining. Sorry?
How are you ordering?
Very good. Very good. What does it mean to say x is greater than equal to y, right? X is also a string, y is also a string. What does it mean that x is greater than equal to y? This is just partial order, and x is greater than equal to y if all the entries of x are greater than all the entries of y coordinate. Make sense? Now you know what x greater than equal to y means. Is x greater than equal to y or not? No, right? Because in some sense, I can change -1 to 1, but I can't change 1 to -1 when I go to an upper string. Right? Another fun thing which you can check, I'm not going to spend time on it, is that this coordinate-wise equivalence or this definition of Norton function remains the same even if you say that -1 is greater than. Right? If in the real numbers, when I say coordinate wise x is greater than equal to 1 means at every coordinate place 1 is greater than -1. But if instead, if I take the opposite definition, I say that this is the biggest string, this is bigger than everything, and 1 1 1 1 is the smallest thing. Even that will give you the same definition of Norton function. So remember, but then fx greater than equal to fy here means -1 is greater than 1. It won't change. It is basically preserving the order. Again, if I look at the Boolean hypercube, let's say this is -1 -1 -1, this is 1 1 1. If I change some 1 to -1, my function value cannot become -1 to 1. The function value can't go in the opposite direction. This is what Norton function definition is.
Can you just repeat how coordinate-wise x is?
So you just compare it coordinate-wise, right? 1 -1 -1
I am missing the words.
-1 -1 -1 is the biggest string, and 1
Sorry,
1 1.
I missed the voice.
No, I'm saying -1 comma -1 comma -1 is the biggest string.
Okay.
And 1 comma 1 comma 1 comma 1 is the smallest.
So you have priority over -1 over 1.
Actually, it doesn't matter. You should just be consistent. If you give priority of 1 over -1, then when I say fx greater than equal to fy, you should again say that 1 is greater than -1. If you give priority of -1 over 1, then even when you, so you have to be consistent in both these. That's my point.
Oh, it is not standardized.
This fx greater than equal to fy is not. Yeah, we can. If in x greater than equal to y, we are saying coordinate wise -1 is greater than 1, then in fx greater than equal to fy, we should also say that -1 is greater than 1. Okay, if we define x greater than y in the opposite way, then fx greater than equal to fy will be the normal real number where 1 is greater than 1.
And one more question I have. I could not get this thing DIF square equal to LIF square because LIF has one more variable. How can they?
Which one?
The what we have written DIF square is same as LIF square.
Right. You look at the definitions. Take it as an exercise.
Oh.
Look at the definition of DIF and LIF. You will see.
So just because I cannot see right now, what was LIF? Fx plus
Fx minus Fx. This is LIF, right? It is written there. Yeah.
Okay.
Okay.
I was asking because LIF has one more variable, so how?
No. DIF now again we are considering DIF as variable over all, a function over all n variables, right? That's what I said. To remove the confusion, all our functions are from n variables to one out. Right? This is what I said. So to remove confusion, think of every function as -1, 1 to the power n to -1, even your DIF, EIF, LIF, all of them, we will view it as these functions. -1, 1 to the power n to -1.
But DIF was defined by replacing.
DIF will be independent of xi.
Replacing one bit, xi bit.
Yeah, it doesn't depend on xi. I can always include an extra variable, on which the thing doesn't depend. That doesn't change my function. How does it matter if I introduce another variable and my function does not depend on that? That is always possible. Right? It won't change anything. With this definition of monotone function, so what can I say about influence of I? Remember, I had said DIF whole square, correct? Influence I of F. But if it is a monotone function, then this is basically expectation of DI. Because your DIF will always be of the same sign. Correct? Since the function is monotone, if f is monotone, then the function will always change in the correct direction. When I take xi to be 1 and then xi to be -1, it can never happen that the value changes from -1 to 1. It will only change from 1 to -1. That means DIF will always be positive if f is monotone. And it's a 1-0 variable, so I don't have this. Now, knowing the Fourier expansion of DIF, what is the expectation of DIF? What was DIF? Right, this was the Fourier expansion of DIF. So what is its expectation? You tell me this and the lecture.
F hat of that particular set, I mean that particular coefficient, where chi of I mean just xi was there.
Right, so that is f hat of I, right? Correct. What is the expectation of a function? It's constant coefficient, right? This is something which we have seen so many times. The expectation of any parity is 0 if that parity is non-trivial. This we have seen so many times. This is Z1 only if S is 1. 0 otherwise. And then this quantity being phi means S is I. So our definition of derivative allows us to give a very, very simple formula for influence of F when F is monotone. Sorry. Many a times people just write it as F at of I. That is just notation. And influence of F is summation over I. For monotone functions, the influence can be written easily.
In the previous page, how do we change from DIF square to DIF?
This we can only change because F is monotone, right? Look at the definition of DIF. Where did I define DIF?
Yes, yes, it
right.
goes from 1, then -1.
Right. So now what we know is that DIF will only be non-zero if f of x I comma 1 is different from f of x I comma -1.
Yes.
What are the possible values? F of x I comma 1 is 1 and f of x I comma -1 is -1.
Yes.
In that case, this will be 1. This is fine.
Yes.
What happens if f of x comma I comma 1 is -1 and f of x comma I comma -1 is 1?
So it will, this change will not hold. DIF square is not equal to DIF.
But this cannot happen because the function is monotone. Right? Because x of I comma 1 is always bigger than x of I comma -1. Suppose 1 is greater than -1.
But if we have chosen that -1 is greater than 1,
sure, you take a definition -1 greater than 1, right?
Yes.
Then that means f of x comma I comma -1, can it be -1?
Okay, okay. It cannot be, okay. Then the first one, that the first argument will not hold.
Right. So f of x, so if you define -1 to be greater than 1, that means f of x I comma -1 will always be greater than equal to f of x I comma 1.
Yes.
Right. That means if f of x comma I comma -1 is 1, then f of x I comma 1 will definitely be. It cannot be -1. So you just look at the definition of monotone and you will see that the other thing is prohibited by the definition of derivative.
Okay, okay, yeah. Okay.
Of monotone, right? So my request is that you look at this definition of monotone the way I have defined it and understand it, right?
But is there some special property for the Fourier coefficients of monotone functions? Because the influence is a probability, so it is definitely greater than equal to 0. So f at I is greater than or equal to 0. But this need not be true for the general Boolean function, right? It could be negative as well. But here it's
right. So this is one of our projects. You look at these special subclasses and try to figure out what does that say about the Fourier coefficients.
Okay.
Right. Like for symmetric functions, we figured out that the Fourier coefficients were all same in the same level.
Yeah.
Now, similarly for monotone functions, we have discovered for first thing. What is that? That the coefficient of xi's are all positive.
The coefficient of xi's are positive.
Or positive,
yeah.
Right? Just now we discovered, right?
Yeah.
So this is something which we keep doing. We want to figure out, characterize the properties, the standard properties. Now fx greater than equal to fy, if x greater than equal to y is given in the standard domain. What does it mean in Fourier? Those are the questions which we